Well, now that we've looked at a little bit of polyprotic dissociation, we're going to take a little bit of a step back, a little bit of review, and a little bit of an extension on some of our earlier knowledge from previous course. And we're going to look at titration calculations. So just as a reminder, an acid-base titration is where you are determining the concentration of one substance, either acid or base, by reacting with another, the other part, either base or an acid. A very common technique used with acids and bases, one of the easiest ways to determine an unknown concentration. One of the more common misconceptions that we have is that anytime you do an acid-base titration, your endpoint is always going to be 7. This is just simply not true. It really depends on what type of situation you have, what type of acid and or base you have. So the only time that you are going to get a pH of 7 is if you have a strong acid being titrated with a strong base or vice versa. If you have a weak acid or a weak base involved, pretty much guarantee that you will not have a pH that is equal to 7 at the end point. So let's look at the simplest situation that we have for titrations. This is a strong acid, strong base. When you add a strong acid to a strong base, you have a 100% reaction upon addition. There is no equilibrium set up. And remember, this is because we have a weak, very weak conjugate acid or conjugate base. When we're doing the calculations, we can work the reaction simply, or the calculation strictly from a standpoint of moles, or a unit that we'll see today is millimoles, a little bit easier to work with. And a lot of times when you are looking at a pH, if you have an incomplete reaction, say you added more strong acid or more strong base or less than was needed to reach your endpoint, in order to find the new pH, you're going to have to recalculate concentrations by recalculating how many moles or millimoles of either the acid or base are left, and then look at the new volume, which has your volume that you started with, plus any of the acid or base that you added into that solution during the titration. So as we've seen in graphs earlier, while you're titrating, if you're titrating an acid into a base, or rather a base into an acid, as you add that base, the pH will rise very slowly until you're nearing your equivalence point. As soon as you get close to your equivalence point, the pH rises very rapidly, passes through the endpoint pH, and at that point, moles of acid that you started with are equal to the moles of base that you've added. And at the equivalence point where those two things are equal, again, you will have a pH of 7, only for this situation where you have a strong acid and strong base being titrated. So let's look at an example, and we'll calculate a pH of the solution before we reach the endpoint of the solution. So we have a 25 milliliter sample of HCl, has a molarity of 0.723. We're going to titrate that with potassium hydroxide, another strong base, that has a concentration of 0.273 molar. So what we want to know is, what is the pH after the addition of 10 milliliters of the potassium hydroxide? So our net ionic reaction is just simply going to be the hydronium ion H3O plus that we get from the HCl, and the hydronium ion concentration initially is going to be 0.723 because it's a strong acid, and the hydroxide that we get from the KOH, strong electrolyte, strong acid, strong base, and we have 10 milliliters of that. So those two things react and we get water. Now we're going to want to work in millimoles, and so the way we work in millimoles is we can just take the molarity times the volume in milliliters, and that will give us millimoles. So for hydronium, we take the 0.723 of HCl, we have 25 mils of it, so we have 18.08 millimoles. And for the hydroxide, we have a molarity of 0.273, we have 10 milliliters of it, and so we have 2.73 millimoles. You can see that we have not added enough base to neutralize all of the acid, which means that we have not yet reached our endpoint. But we still want to be able to calculate the pH at our stopping point for the titration here. Where are we after 10 milliliters? So we can set up a simple icebox here. Even though this is a strong acid, strong base, we can kind of change the meaning of the E. It's not really equilibrium at this point. You can think of it as end. This is where the reaction ends after you've titrated your volume in there. So our initial number of millimoles of H3O plus was 18.08. Our initial of hydroxide is 2.73. They are going to completely react 100% and going to react until one of them is done. And so you can look at the values. We have 18.08, 2.73. They react 1 to 1. And so all of that OH minus is going to get used up, and it's going to use up the exact same number of millimoles of H3O plus, again, because they react in a 1 to 1 ratio. And so what we have left here is 15.35 millimoles of H3O plus at the end. It's just this minus this, and we get 15.35. Our hydroxide is going to be completely reacted. There's not going to be any hydroxide left in that solution from the added KOH. So now what we need to do is we need to calculate a new concentration of H3O plus that's in the solution. We have a new volume. This is one of the things that a lot of people forget to do. We have a new volume of 35 milliliters because we had a 25 milliliter sample that we started with. We added 10 milliliters of KOH. So now we have 35 milliliters of solution. So we always do number of moles. So for our molarity, we can take our millimoles and put it over our milliliters. So that would be 15.35 divided by our new volume, 35.00, and we get a new H3O plus concentration of 0.439. And if we take the negative log of that to get the pH, we get still a very low pH of 0.36. Now, at the equivalence point of a titration, that's where the moles of acid are equal to the moles of added base, or vice versa. It just depends on what you're titrating with. So at the equivalence point, both your acid and your base are neutralized. So you have none of the original acid or the original base, and you have none of the added base or added acid. So if we take a look at a solution here, how many milliliters of 0.61 molar sodium hydroxide are needed to neutralize 20 milliliters of 0.245 molar HCl? We can look at our reaction here. We've got HCl plus NaOH. The H and the OH are going to react and give us H2O, and we're going to have NaCl aqueous left. So remember that aqueous tells us we're going to have sodium ions and chloride ions. So they're not actually going to be bonded together in an ionic compound because sodium chloride is fully soluble. So we're going to have sodium ions and chloride ions in there. So we want to know, what's it going to take to reach our endpoint? How much are we going to need to neutralize the acid of HCl? So we know that at the endpoint, our moles of acid have to equal our moles of added base, or we can also say millimoles of acid equals millimoles of our added base. So to calculate the millimoles of our acid, we can take the molarity times the milliliters. That's going to equal the concentration of our base times the volume of base that we're going to need. Now this we don't know. And so we're going to have to calculate that. So we just calculate our volumes here, divide by our molarity of our base here, and we get a value of 8.03 milliliters of NaOH. Now, if you're not comfortable working in milliliters and millimoles, that's fine. You can use liters here, and you'll get your answer out in liters here. You'll just have to reconvert into milliliters depending on what the answer is looking for. But a volume is a volume. So this is why I find millimoles easier to work with in these types of equations, because we don't have to convert between milliliters and liters all the time. Now, if you have a stoichiometry up here coming from your balanced reaction, that's not 1-to-1. Notice that we have a 1-to-1 HCl to NaOH. If you have a polyprotic acid or a polybasic base, then your stoichiometry here in this equation is going to be a little bit different. So you always have to take that into account. Now, at the equivalence point of titration, the only thing that's left is water and a salt. in that last equation, or that last reaction, we saw that the salt that we had was sodium chloride. Remember, a salt is just a cation and anion that come together. So that's your salt. Now, when you have that strong acid, strong base titration, as I mentioned earlier, the salt that results from a strong acid, strong base titration has no acid-base properties, and therefore the solution is neutral. So you have a neutral salt with water, no pH change from neutral, so that's 7. If, however, you have a weak acid being titrated with a strong base, then the salt that you're going to have at the end will be the conjugate base of the weak acid and the conjugate counterion of your strong base, which never has any acid-base qualities. And so if you have that weak acid, the salt will contain that conjugate base of the weak acid. And as a result, you're going to have a basic solution. An equivalence point will occur at a basic pH. So let's take a look at an example here. We have sodium hydroxide getting reacted with acetic acid. So here we have a strong base, NaOH, with a weak acid, HAC, acetic acid. When that reacts, you're going to get water resulting from the H and the OH reacting. You're going to get sodium acetate, which is going to be aqueous in water. So really what you're going to have is you're going to have acetate ions and sodium ions. That acetate ion, because it's the conjugate base of a weak acid, it itself will be a weak base and will have base properties and will hydrolyze in water. So it will react with water as a base. So let's look at an example. We're going to look at a titration of acetic acid. We're going to titrate it with sodium hydroxide, and we are going to look at the pH of the titration at 3 different points. Now we can see that we have 25 milliliters of 0.1 acetic acid, and we're titrating with 0.1 molar NaOH. So even though this is a weak acid and this is a strong base, it's still a 1-to-1 reaction. And so because their concentrations are identical, their volumes will be identical at the endpoint. So it will take 25 milliliters right here for B. It will take 25 milliliters in order to neutralize the acetic acid with the base sodium hydroxide. So what we have here is we have a point before our endpoint. We have a calculation right at the endpoint, and then we have calculation that comes after the endpoint. So some things to consider as we do these calculations. Each calculation for each volume can be done completely independently. So you don't have to take the result of the calculation for A and then use results for the calculation for B and then the calculation for C. We can do each one independently, assuming that each one would be a separate titration just going to that volume. Anytime you're doing a calculation and you're looking at moles, you have to take a look at your changing volume. You have to look at what's my new volume, because you may have to calculate a new concentration. And if you only know the number of moles, to get the concentration, you need the volume. So you need that total volume, and it does change as you go through a titration. And then after our equivalence point, so after that 25 milliliters, the only thing that's really going to determine the pH is the additional OH minus from the strong base that you're adding. You do get a small base contribution from the conjugate base of the weak acid, but as we'll see, its contribution is going to be extremely small compared to added strong base from the titration. All right, so let's start this first one, 10 milliliters of added base. So the first thing that we'll do is we'll need to calculate the number of millimoles of each substance. We'll set up an ice box where we're reacting the strong base with the weak acid. We need to do that before we consider any equilibrium. The equilibrium will set up after you have a strong base or strong acid reaction with your weak titrant in the flask. So when we react our weak acid, so acetic acid, down the flask, we add some strong base. It's going to react. That strong base is going to pull the H off that weak acid. It's going to give us H2O and leave us with a little bit of acetate still in that solution. Okay, if we look at the number of millimoles of each, we have 2.5 millimoles of our acid. We've added 10 milliliters of 0.1 of our base, so we've only got 0.1 millimoles of that. Because it is a 1-to-1 reaction, the 1 millimole of our strong base is only going to be able to neutralize 1 millimole of our weak acid. So we set up the icebox like that. And again, this is kind of anytime you have a strong thing, it's going to be initial change and end as opposed to equilibrium. We have no equilibrium here. Notice the arrow. So we have 2.5 millimoles of the acetic acid. We have 1 millimole of our base. We have no acetate to start. We know that it's going to change by 1 because we know how much base that we have and all of it's going to react. So we're going to lose 1 millimole of our acetic acid. We're going to lose all 1 millimole of our base. It's going to make 1 millimole of our acetate because we have a 1-to-1 ratio here. So what we're left with after that reaction takes place is we have 1.5 millimoles of our acetic acid and we have 1 millimole of our acetate. Now we can plug these millimoles into our Henderson-Hasselbalch equation. Because we have a significant amount of a weak acid and its conjugate base, we can say that we do have a buffer solution here. So you may want to review buffer solutions from our previous course. Remember, you have to have a significant amount of your weak acid and its conjugate weak base. As long as they're present in something stronger than a 10-to-1 ratio, then you have a buffer solution. And 1 and 1.5 is well within a 10-to-1 ratio. So we have our Ka. We need to calculate the pKa by doing a negative log. And for this one, it's 4.74. For this reaction, you can calculate the concentration of the conjugate base and the concentration of the conjugate acid if you would like. But because you're going to be dividing these by the exact same volume, the ratio of the concentrations will be the exact same as the ratio of the millimoles in this case. So we can just plug in our values for the millimoles. This is our equilibrium that we have taking place in case you're wondering which is the acid and which is the base. Remember that your Henderson-Hasselbalch equation is still set up as products over reactants. And so our product is the acetate ion, our reactant is the HAC. So we plug in those values. We have the 4.74 for our pKa, and our log will be concentration of the base, the acetate ion at 1, over the concentration of our acid, our HAC at 1.5. And when we calculate that out, we get a pH of 4.56. So after adding 10 milliliters of strong base, we're going to now have a pH of 4.56. Let's move on to the next volume. So this is at the equivalence point, 25 milliliters of added base. So again, we can take this calculation from the start, so we don't have to worry about the 10 milliliter calculation at all. Now again, this represents our equivalence point. We have the exact same number of moles of acid and base, and we know this because we have the same volume of two solutions that have the same concentration. So at the endpoint, only the conjugate base, the acetate ion, will remain because the acid and the base that are reacting have completely neutralized each other. So there'll be no more OH minus from the sodium hydroxide. There'll be no more acetic acid because it's been neutralized. So when we have that conjugate base of a weak acid, it will act as a base in water. It will hydrolyze and give a basic solution. So because we have a base reacting with water, we need to use Kb and not Ka. Okay, so here we can find, using an icebox, we can find what is the concentration of our acetate ion. So first thing we'll do is figure out how many millimoles of acetate do we have. Well, again, we take our milliliters times our molarity to get millimoles, and we get 2.5 or 2.50. So we have 2.50 millimoles of acetic acid. We have 2.50 millimoles of hydroxide, and at the start we have no moles of acetate. All of these moles of acetate and hydroxide are going to react with each other, and we're going to have none left at the end of that reaction. Again, it's an end. We have a one-way arrow because we have a strong base. Anytime you have strong acid or strong base present in a reaction, it's always going to have a one-way arrow. Now, these two things react and they form 2.5 millimoles of my acetate. Now we know that the acetate is going to react in water because it's a weak base. So we're going to have acetate plus water going to HAC plus hydroxide. This hydroxide is why we're going to have a basic reaction, and the base reaction with water is why we need to have a Kb. This is a Kb equilibrium. Now, to get the concentration of our acetate ion, we have 2.5 millimoles that we got here. Our new volume is 50 milliliters because we have 25 milliliters of the original acid, and then we've added 25 milliliters of our base. So our new volume in our solution is 50 milliliters. So 2.5 divided by 50 milliliters gives me a new molarity of 0.05 molar. Now I can set up another ice box based on this equilibrium here. And so I'll have 0.05 for my acetate. There's no HC left from the original reaction. There's no OH minus left in the original reaction either. Because it's an equilibrium and we're working with a weak base, we don't know how much change is going to take place. So some of this acetate is going to react with water and form X amount of HAC and X amount of OH minus. We're going to lose X amount of the acetate. So we have 0.05 minus X, X, and X. Remember to calculate the Kb. We know that the Ka times the Kb is equal to our Kw for a conjugate pair. Kw is 1.0 times 10 to the minus 14. And so our Ka was given in an earlier slide, so you should be able to calculate the Kb and get 5.56 times 10 to the minus 10. So our Kb is going to be equal to our concentration of products over reactants. So we have concentration of HAC times concentration of OH minus over the concentration of the AC minus. So we have X times X over 0.05 minus X. We have a very small Kb. We can assume that that X is going to be very tiny, so we can ignore that, solve for the X's up here, and we get an X value of 5.27 times 10 to the minus 6. And if we look at our ice box, it shows that X is equal to the value of the concentration of hydroxide. So that allows us to calculate a pOH. Taking the negative log of the OH gives us a pOH of 5.28, but we want a pH, so we need to subtract that value from 14, and we get a pH of 8.72. Remember, we said if we have a weak acid being titrated with a strong base, we're going to have a weak conjugate base at the end point, and we're going to have a basic pH, and that is in fact what we have. We have a pH of 8.72 at the end point. All right, now we're going to go past our equivalence point, and we're going to add 10 more milliliters of strong base. So at this point, the only thing we're doing is adding additional strong base. That's just going to make the solution more basic. Because strong bases dissolve or dissociate completely, every bit of base that we're adding is going to affect the pH. Whereas you're going to have a little bit of contribution from the acetate, but we saw in that previous slide, it contributes a very low concentration of hydroxide ions into that solution, much less than what the sodium hydroxide that you add in is going to contribute. So again, we kind of start from the very beginning. We're going to add 35 milliliters of our strong base. We start with 25 milliliters of our acetic acid. So we have 2.5 millimoles of acetic acid, 3.5 millimoles of hydroxide, because you have 35 milliliters times 0.1, the concentration, so 3.5, and we have 0 millimoles of acetate at the very beginning. Now our limiting reactant here becomes our acetic acid because it has the lowest value of anything being added. So we're going to lose all of the acetic acid. We're going to lose 2.5 of the hydroxide as well because it is still a 1-to-1 reaction. So they're going to lose the exact same amount. And I'm going to gain 2.5 millimoles of the acetate. So at the 35 milliliter point, I'm going to have 1 millimole of hydroxide left over, and we're going to have 2.5 millimoles of the acetate. Now, again, we saw in that previous example how little this amount of acetate hydrolyzes in solution, and it just does not produce very much OH minus. So we're going to ignore the acetate in this case. So what we have is 1 millimole of hydroxide. It is in 60 milliliters of solution because I had 25 milliliters of the acid and 35 milliliters of the base added. That's 60 milliliters. So that gives me a concentration of hydroxide of 0.01667. And from that, I can just take the negative log to get the pOH at 1.78, and that gives me a pH of 12.22. Now, when we're titrating polyprotic acids, it becomes quite a bit more complex. Really what you have is you have two separate titrations taking place. While you're adding strong base to a weak acid that's polyprotic, you're first going to go through that Ka1, that first equivalence point. And so that's going to occur at some pH based on the value of that Ka1. Okay, so if you had, let's say you had 25 milliliters of a 0.1 solution of polyprotic acid, and you were titrating it with the exact same concentration of base, something like sodium hydroxide. So same as with a monoprotic acid, the volume needed to reach that first endpoint is going to be the exact same. So if the concentrations are the same, if you had 25 milliliters of acid, it would take 25 milliliters of base to reach that endpoint. Now, once you do that, you're going to produce the same number of millimoles of the second acid, the second acidic species in there. And so you have to add the exact same amount of base to take off the second proton off of there, because you have the exact same number of moles of the secondary acid that's in that polyprotic acid in order to reach the second equivalence point. So in theory, if it takes 25 milliliters to reach the first endpoint, it's going to take 25 milliliters to reach the second endpoint. Now, in practice, sometimes different things can happen because you can run into some kinetic issues, you can run into some thermodynamics issues, and it doesn't always go quite as well as you hope, but it's usually fairly close. So again, your first hydrogen journey comes off at a fairly low pH. Each successive equivalence point will be at a higher pH as that Ka decreases, because you have to add more and more base in order to get that subsequent H plus off of that new anion.